And today we're very happy to have with us Dr. Gurpal Toor and Charles Burgis. They both work in, I'll say, nutrient management, water quality in the Mid-Atlantic and beyond some, and they've agreed to step in and provide this presentation today, and we understand that it will be a tag team. And so I believe Dr. Toor is going to start, and then at some point he'll hand over to Dr. Burgis, and we'll see how it goes. So Gurpal, thanks for joining us today.
All right, thanks, Marty. I'm very happy to be here. Welcome to our Wednesday seminar. Also, welcome to our out of Maryland folks here who found time to be here. So we've been working quite a bit in the last 2 years, and with COVID, we thought it will be a good time to actually share what we have been working secretly or in isolation. So this is the sort of a combined effort of some of the work that has been gone on to this a very complex and difficult, I will say, set of projects that we are pursuing. Let's see. So there are a bunch of people I want to acknowledge. Without their support, it's hard to do field research in general, but especially when it's a complicated field research. So a bunch of people that you see, Charles, he's been here almost a year and a half, and we're very fortunate to have an opportunity to work with him. Shuang Duong, he's been here. These are our two main field guys who are out in the field every week and then driving 500 to 700 miles each week. Bradley Kennedy, she's a new PhD student. She's providing support to the field activities as well as lab efforts. Fazine, she's our lab manager. She's making sure all the samples are taken care. We also have Trish Steenhelber. Many of you know she retired a few years ago. Through some arrangement with MDA, we were able to hire her back, so she's providing some critical support with some components of the project. Emily is already sort of getting her feet wet in this arena. She's going to be starting PhD in the fall. Taylor Roswell, many of you know she graduated, but she's so good, so we had to hire her back. We also have two awesome undergrad research assistants that we hired in the last 6 months, Quinn and Autumn. And two former members, Unea Yang, who left us earlier this year, sort of started parts of this project when she came on board about 4 years ago. And many of you know Stan. He retired, but he was an animal in the lab in terms of our analysis. And of course, none of these things would have been possible without the generous funding support from agencies. So I want to acknowledge Harry Hughes Center initially to fund parts of the project, and MDA funded a huge chunk of this project. We have 3 NEFA grants supporting these projects, and we have an EPA grant also sort of dovetailing with some aspects of it. So what we're going to do today is we have 5 parts in this presentation. So I'm going to cover, as Marty alluded to, part 1 and 2. At that point, I'm going to stop sharing and Charles will switch over. He will share slides and talk about number 3 and 4, and then I will conclude with the last part of section. So the goal of this exercise is first to share what we are doing, but as you are sort of looking at what we have done, I want you to think critically to see if you see any opportunities for collaboration. So one of my sort of central goal with this project is to share with the department what we are doing and see if there are any ideas for sort of cross-disciplinary collaboration, not even with the department, but with our other colleagues out of Maryland as well. So just to make sure everyone is on the same page, so you are in Chesapeake Bay Watershed, welcome. This is one of the, a huge watershed, 64,000 square miles, more than 18 million people live in the watershed. This is also the largest estuary in the US and 3rd largest in the world. This is a primarily agricultural sort of a watershed. There's about a quarter of the total land in watershed is agriculture. There's also a lot of forest area. Don't pay attention to the colors because the colors on the left are have a different meaning than colors on the right. So you see all the yellow on the left, that's all your agriculture. On the right side, these are some of the big watersheds within the Chesapeake Bay watershed. And in those watersheds, the range of agricultural land use is anywhere from 13 to 48%. If you are in Maryland, Choptank, this is on the eastern shore of the Maryland. This is our biggest watershed. And also half of that land area in this watershed is agriculture. So agriculture is predominant, as we all know, in this area. So we also know, and some other folks out of state may not know, but nutrients, they drive the policy in the Chesapeake Bay watershed. And there are sort of several compelling reasons we need nutrients to grow food. They're essential for plant production. And I think that's the challenge when they leave the field, get into water body, that's where they become pollutants. So how do we manage on the land so that they don't run to water bodies? That's our goal of our research. Just to put things in bigger context, we are not the only water body that's polluted. In fact, there are more than 14,000 water bodies in the US impaired with nutrients and river streams and lake acres and estuarine, other areas. So when we look at sort of model, this is again modeling exercise done by the Chesapeake Bay program through their model. If we look at the total nitrogen loads, there are a few things that stand out. Like, so if you look at nitrogen, you see agriculture is a huge source. These bars are over 3 time periods. So you're looking from 1985 to 2020. So we are making progress in reducing nitrogen from agriculture, which is blue, but not so much. You see there's a major sort of decrease in wastewater, many efforts with wastewater treatment upgrades, Clean Water Act. So we are doing really good in terms of reducing nitrogen loading from wastewater. Another thing you see is developed land. This is urban land area that many of in our department work on. We see that that area is also increasing, and that's also contributing more polluted runoff from urban areas. So when we look on the phosphorus side of the scale, you kind of see similar pattern: agricultural, wastewater as 2 dominant sources, developed land as another major sources. One thing that you see with phosphorus more clearly, that over the last 30 years, the contribution from wastewater has been declining. This is again Clean Water Act, more NPDES permits that the wastewater treatment utilities are required. So good progress in agriculture. We are making progress, but we are making slow progress over the years. So just to another kind of slide, that how much nitrogen are we losing, from the fields? Like, so this is a map that's based on sub-basins, and this is again, the units are different, but I'm going to try simplifying here. So if you look, most of the colors are somewhere between orange to sort of dark brown. That's where most of the sort of sub-basins in the whole Chesapeake Bay watershed are, including parts of Maryland. So we see that in most fields on this slide, most of the farm fields are losing about 9 pounds of nitrogen to more than 16 pounds per acre. So this 16 is where I think it doesn't go beyond that. Some of the other data that we see, this number easily approaches 40, 50 pounds per acre, which is quite a bit of nitrogen. A farmer typically for corn production will use about 200 pounds of nitrogen per acre. So if you're losing 20, 30, 40 pounds, that's an economic loss to the farmer. So again, like most fields, I think you can say that 14 to about 15 pounds per acre of nitrogen loss from those fields. So when we look at phosphorus, this is where I think the story of Maryland get interesting. And you see that's where the red colors in all Maryland sub-basins pop up, which means this is where most of the phosphorus is lost from Maryland. So if you're looking at all the reds or combinations, you're looking at anywhere from 6 to 10 pounds of nitrogen per acre, which is quite a bit of phosphorus. Just to kind of, give a bigger context, if you look at most of the word soils, and typically phosphorus loss is about 1 pound per acre. So this is very high, and we know that we are also intensive animal agriculture. So there are many compelling reasons why this is higher on the right side in the Eastern Shore. That's where we have poultry industry. There's 600 million chickens grown each year worth billions of dollars. So the chickens are interesting in a way. If you don't know the story, chickens like us, they need food, right? But we don't have enough land mass. to grow corn and soybean that we feed them. So that stuff is grown in Midwest, imported to Eastern Shore to feed the chickens. After chickens eat, they leave manure locally. So then it becomes a localized problem, and that manure is land applied. And this didn't happen overnight. This happened over decades of application of poultry manure. Our soils are super saturated with phosphorus, many of the soils. And as a result, we also have higher losses from some of those areas. Most of our state regulations are on phosphorus. This is managing phosphorus. What could be done to either reduce levels of phosphorus? This is where our whole agriculture nutrient management program comes into play. And I'm sure many of you already are familiar with that program. If not, quickly Google Ag Nutrient Management Program, and you will see that we have a really great program funded through EPA via MDA that supports several extension specialists that are based in the counties. They help farmers develop nutrient management plans. Again, those are directed main to manage phosphorus, but also take into consideration other aspects such as nitrogen. So in Maryland, we lose quite a bit of phosphorus. We're looking at 6 to 10 pounds per acre. So this is really a simple way to sort of look at it. What are we trying to do? You know, we're trying to collect the farm field data so that we can understand how, when, and why nutrients are lost. Or if you like more scientific jargons, I can say we are looking at processes and mechanisms and drivers of nutrients and carbon loss from those fields. And there are several reasons we want to do that. We want to sort of, if we can figure that out, then we can develop best management practices to keep these nutrients and carbon in the farm field. And an ultimate goal with one of our main MDA project is actually to develop a next generation of phosphorus tool that we could use. But we're also interested in expanding to another nutrients, not necessarily to manage farmers, but more importantly, what can we actually tell them so that they can go on and do things on their farm fields that result in more nutrients in the farm fields that they need to. So switching over to catchment selections. So if you're familiar with the map on the right side, this is for TMDL purposes. In the Chesapeake Bay, Maryland is divided into 5 subbasins. So all the eastern shore is one subbasin. And on the left, there's a western shore. Once you go all the way into the western part of the state, that's where Potomac is, which goes through DC. And then somewhere here, we have Patuxent in the middle. There's a little bit of Susquehanna, the watershed that's in Maryland. Most of that is in Pennsylvania. Another way to sort of look at would be that the state of Maryland is divided into 133 subbasins. So these are what's called 8-digit hydrologic unit codes. This is USGS classification system on classifying watersheds. So in the whole country, there are about 2,200 HUC codes, just to put a bigger picture. So we have these. This is more manageable. So think about these HUC codes are like your address, like, so you can actually go and search your watershed and find what's actually is out and what type of data exists. A really great website from EPA on that. Okay, coming back to Maryland. So, you know, Maryland is not a huge, we don't have a whole lot of land mass to begin with. Like, so we have about 1.2 million acres under agriculture. We have about same acreage under turf grass production. But if we look within the agricultural crops, we have about 500,000 acres under corn, again, another 500,000 under soybean. And then we also have another 300 plus acres under winter wheat. So all these things, corn and soybean, happen during the growing season, which is beginning right now through October. And then winter wheat is a little late. Cover crops are always in winter. So we have about 400 plus acres under cover crops. And if you don't know, state of Maryland also has a cover crop program where farmers are provided cost share to grow cover crops. And this is again to help with the nutrient loading, primarily with the nitrogen loss and also erosion. So there was a lot of time, Brian Kalmbach and Trish Steinhelber, they spend a ton of time. This is pre-COVID. So when we sort of started looking at sort of developing this type of projects, we just didn't want to find a field that exists because we know the farmer or we know someone who knows the farmer. So we wanted to really use a comprehensive approach. So our experimental design is as rigorous as possible. So in that pursuit, this is University of Maryland Extension again with the nutrient management program. Our advisors, they develop plans for different farms throughout the state. So Trish and Brian, they looked into each of those fields. And in this case, we were looking for those fields that have high phosphorus level, and which means that when the phosphorus level is high, farmers have to use a regulatory tool. In this example, this is a phosphorus site index. So on that basis, we started going by county to see how many those fields qualify under that criteria. Like, so when we looked into that, when they looked into that, we found there are more than 200 fields in the western part of the state. And then on the eastern shore, that's where we know we have more fields. So once we had that, and then Brian come back, this map doesn't really do justice, but these are those 832 dots that we threw on a Maryland map to see where are they sort of scattered throughout the state. And then we use some another criteria. For example, the soil phosphorus level needs to be more than 150 milligram per kilogram, a Malik 3 level. So once we use some other criteria, drainage, for example, this was not just a field we were looking for. We were really looking for a catchment that we can monitor. So many of the fields were great, but they didn't met our criteria, didn't qualify us to do what we wanted to do. So out of these 800 fields, we found that there were about 130 fields that met our initial criteria. And that's when Charles came on board in July or August of 2020. And Charles, along with Shuang, they started making the catchment maps. We started looking at a lot of fields to see which of these fields will actually work for us. And we spent probably, I would say, Charles, 6 to 8 months, if not a year, in terms of getting to where we wanted to be. So on that basis, we identified the 5 catchments in the western part of the state that we think are going to work best for us. And then we found another 10 on the eastern shore. Again, like there are a couple of different ways to look at it. We can look at the PS site fields. This is phosphorus site index fields. We were covering 2% of the fields on each side of the state, so to speak. So what are those field sites look like? So these are the 15 catchments that Charles Shuang have instrumented over the last 18 months or so. So we have 5 sort of these catchments, what we call naturally draining, and these are located in the 5 counties in the western part of the state, from Frederick all the way to Charles County. And once we cross the bridge and go on the right side, in the middle, you see a bigger cluster. This is the mid shore of Eastern Shore. This is where tile drainage is very prominent. So we have several sites that are under tile drainage. And once you go to the lower part of the state, this is the lower shore or the lower Eastern Shore. This is where the sort of, in this case, your landscape is uniquely different. This is where ditches come into play. So if you, another way to look at it will be flow paths, right? So how does water leave a field and get into the bay? So on the natural draining, it's always surface runoff. Once you get to the tile drainage, there's a network of tile drainage that drain the field, and then the tile drainage, they will drain to some part of the ditch directly or another part of the stream network. And the ditch drainage system is an open ditch. It starts at a farm ditch, then it's connected with another text ditch, and then those ditches are connected with the stream network. But everything is hydrologically connected, more so with the tile drainage and the ditch drainage systems. Another way to sort of look at would be going back into the HUC codes, the hydrologic unit codes. So this is like another map that Charles prepared recently. So we were like, let's look at where are we with our sort of catchments. So we are sort of representing 9 of those HUC watersheds areas in different parts of the state. And this gives us some unique perspectives and opportunities. And those in the state know that once you're on the right side where Newport, Bay, 14, 15, this is almost Ocean City, like so very close to ocean. Once you get all the way to number 1, which is our Frederick, the western side. So in this case, we are not only have a climatic gradient, we also have the soils gradient. In this case, you can look at geographical regions in the Maryland. So we have different soil types. We also have different management. We also have different climate along with other factors. So this gives sort of opportunities to sort of look at the fluxes through different parts of the state as determined by other variables on the field. So some of the sort of management options for these fields, again, these are those 15 sites, and the left is all the counties. Then the next column that you see is the soil phosphorus level. So the soil phosphorus level, this is what we call plant available phosphorus. And in state of Maryland and in other states, we use a test called Malik-3 phosphorus. So this was one of our criteria that fields they need to be more than 150 milligram. So again, that's what when we started selecting those fields, you see we have few fields and tile drainage that were below that threshold. So we also wanted to sort of see how does these losses differ in other fields that are not yet supersaturated. And just a reminder, in state of Maryland, if this soil phosphorus level is more than 150, no phosphorus application from manure or fertilizer are allowed, unless the farmer runs a regulatory tool. And right now we use phosphorus management tool to see if they can apply more manure or phosphorus in this case. And some of these field sites, once you get on the lower shore, this is not a surprise. There's another pet word that we're using. It's called legacy phosphorus, which means these fields reflect a legacy of long-term application. And as a result, phosphorus level is very high. Another point here, typically when this level is less than 100, 50 to 100, we do not recommend any phosphorus application because there's no benefit in terms of plant uptake. So your yield is not going to increase if this level is more than 100, but we have a cutoff at 150. And again, just follow the colors here: blue for natural drain, green for tile, red for ditch. Okay, so what's been grown in these catchments, right? So, so in this case, primarily it's an agricultural watershed where we see a rotation. Either it's corn in the first year, and then there might be cover crop in the winter. Next year, the farmer will have soybean or combination. We also have an interesting sort of catchment where a part of the sort of catchment is strawberries. This is Anne Arundel County, close to Annapolis, so there's a good reason to be. We also have another catchment somewhere in Caroline where we have it's one of our biggest catchments, but there's alfalfa. This is a dairy farm. So if you're a dairy farm, farmer will grow a crop like alfalfa so they can harvest and feed the cows. But primarily, it's pretty much corn, soybean all over in these catchments. Okay, so the next thing is manure use, right? So that's one of our other criteria. So in the two catchments that we're looking at where phosphorus level is 100, those fields, they receive poultry litter because legally they can, and they can use it because the crops actually can benefit from phosphorus application. And this is where irrigation comes into play. Right, so if you're in central part of Maryland, we don't have a huge acreage under irrigation, but you often see the central pivot irrigation system that is used to irrigate, and there's a good reason. Some farmers get subsidies or have gotten subsidies to place that type of network and infrastructure on the field. And if they do that in some soils, especially sandy soils, you can actually have a little bit more yield, anywhere depending on 50 to 100 bushels, which is quite significant for many farmers. In one of our side, this is a dairy farm, so there's also a dairy effluent that farmer uses, and this dairy effluent is actually also fed through the irrigation system and sprayed on the field. So very interesting site. And we have another site, and we're still investigating, but that field somehow got manure, so we don't know if this was an error, but we're investigating that. This shouldn't have gotten any. Again, and the flow pathway here is surface runoff, tile drainage, and surface ditch system. And this is my last slide before Charles take over. So some other hydrological characteristics of these 15 catchments, right? So drainage area is pretty critical, like we need to know. And you can see that many of the sites are somewhere less than, I would say, 10 acres per acre, which is a typical farm field under the sort of management by the same farmer. And we are just looking at a drainage area where the catchment is, not necessarily the field. We also have some pretty huge catchments in Caroline County. Number 9, for example, if we're looking at the largest catchment, very complicated catchment, and Charles is going to talk more about it. And then we have few in the sort of the lower shore of Maryland. Now, this is another way to sort of look at what's the slope in the catchment, right? So we know if there's a more slope, then you can see how the water is going to run off on the surface. And once you get on the eastern shore with Caroline, this is a flat landscape. And all the greens are tile drainage. So there's not a whole lot of elevation within the field. And that's the reason why there's a tile drainage to begin with. Once you go into the lower shore, this is Somerset and Worcester. This is where, again, very flat topography and ditches. And you will see some pictures that Charles will show. Like, oh, so this is actually my very interesting column to look at it. This is the outlet. So in each catchment, we have an outlet. Like, so Charles calculated what's the mean sea level of that outlet. And you can see a very nice gradient as you go from Frederick, and we know that's where we have high elevation. But by the time you get into the lower shore, it's very, very close to sea level. So that presents some other opportunity to explore some interesting questions with nutrient fluxes and exchange. So sampling these catchments is messy, as Charles will tell you, and there's no standardized way. How would you actually take samples from these field sites? So many people, just for convenience, they will say, okay, they will grab one sample once 1 millimeter of runoff has passed through their outlet. And in some cases, you know, it works for some people. In some areas, we are actually below that 1 millimeter threshold, except in few where there's a lot of sort of flux, a lot of water moving. And Charles is going to dig a little bit more into this question with some of the other slides that he's going to show. So I think I'm going to stop here and stop sharing. And Charles, if you're ready, you can start sharing.
Great, thanks, Gurpal. And thanks to the department for the opportunity to speak with you all today. I'm just going to upload my slides here. All right, so I'm going to pick up here talking about the construction and the design and construction of this large monitoring network. And so what we did is we took these 15 different fields of interest, these catchments of interest, and we did some watershed characterization to determine the peak discharge. We estimated peak discharge coming from each catchment so that we can determine the size of our monitoring equipment needed. So what we did is we took, we downloaded a digital elevation model data, which is derived from LiDAR data, which is essentially a digital topographic map of a field or any land surface on the earth. And we overlaid that with our fields of interest, and we were able to delineate the drainage areas leaving a certain part of the field on the edge of each field. We're also able to determine the area, the longest flow path, the slope, and other hydrologic characteristics of the watersheds. And we used the rational formula to estimate peak discharge and then size the equipment we would need to monitor the runoff leaving the field.
Hey, Charles, sorry to interrupt. Can you do the slideshow?
Oh, yes, of course. Yeah, thank you.
Sorry for the interruption.
So yeah, here's the animation that was supposed to appear, excuse me. And so then we actually visited the fields to confirm the drainage pathways. And so here's an example of a field in PG County we visited fall of 2020. And you can see this location on the right. There's a video here that will show, confirm that runoff is leaving where we thought it would be leaving based on the modeling and the watershed maps. We then went in, and once we had the drainage pathways confirmed, we went in and we built the monitoring stations. So this is an example of Flume Installation, which we have, we're using H flumes on our western naturally draining sites. And so an H flume is essentially an engineered channel where if you know the water level, the level of water in the flume, you can calculate the flow rate of the water based on an empirically derived equation. So what we did is we installed concrete pads underneath the area we wanted to place our H flume, right where at the outlet of the catchment, and then we anchored in the H flume shown here in the middle picture onto the concrete pads. We also installed wing walls made of aluminum sheet metal to direct runoff water into the H flume. And then you can see what a finished site looks like. This is in PG County again. Here we have the H flume. At the edge of the field, we have the water level sensor, which is a pressure transducer, which measures the level of water in the H flume. That information is sent into that box where there's an auto sampler, and the auto sampler can calculate the flow rate of the runoff based on the level of water in the flume, and it can then take samples throughout the storm. It's important to take samples throughout the storm, as there's a good deal of change that can happen in terms of the water chemistry throughout a storm. We have a rain gauge, and it's all solar powered. So here's a look at what it looks like inside of our equipment box here. And so we're using ISCO auto samplers with 24 bottles to take flow weighted samples throughout a storm. Now the flow weighted samples, they are samples that are taken in equal volume increments throughout a storm. So there's different ways of doing stormwater sampling. We're doing flow weighted sampling because we want to be able to take samples at equal volume increments because runoff can be unpredictable. We don't necessarily want to do it by time because we don't know exactly when or how long the runoff peaks will last. We want to do it by volume so that we can take samples at equal volume increments and really capture the peaks. We want to capture the peaks. So you can see here in the figure in the bottom left of the slide here, this is a graph of flow rate over time in blue. And then the green circles are showing just the time that a sample was taken throughout a storm. And the green circles are arbitrarily placed on the y-axis, but their position on the x-axis is showing their time. And you can see that during higher periods of flow rate, we're taking samples more frequently than at lower periods. And that's how the sampling works. We're trying to capture the complete peak of runoff throughout each storm with our 24 bottles. All right, so here's an example on the eastern shore now. That was our naturally draining site. This is a ditch site. It's actually a combination of ditch and tile. So what we have here is a very large catchment. It's almost really the size of a whole watershed. And we have 140 acres that's draining from different land use. The map on the left is showing land use, mostly corn, soybean, a little bit of alfalfa in reddish orange on the left. And there's tile drains that are conveying water into a central ditch in pink. Now the ditch moves down to the upper left of the map, and in dark green there, turquoise, that's the outlet of the watershed of the catchment. And that is where this picture was taken of the farm field. And at that outlet, we have, instead of an H flume, what we're using is a water level control structure, which is a box with a pipe that runs through it, essentially that conveys stormwater coming from the ditch. And we pass that through a V-notch weir. Here you can see a 120-degree V-notch weir. And there's a special equation that lets us calculate the flow rate of water over the V-notch weir based on the level of water. We also have a sampler line and a submerged probe, similarly to how we were using measuring water level in the H flumes. We're using the same submerged probes and auto samplers to take samples and measure water level. So that's how it works on the eastern shore for all of our sites. Okay, now I'll talk a little bit about data, some preliminary data we have. Here's a watershed map of our PG County site. Again, it's about 6 acres, about 4% slope, 364 soil phosphorus, FIV, corn soybean rotation. So what does it look like when a storm passes through the monitoring station? So here's a video I'll play. Now you can see this camera was placed here and it's taking pictures every 10 minutes. And if you look at the flume, you'll see some water pass through. This was last summer. It may lag a little bit. And okay, it's freezing just a little bit, but just gonna keep clicking. Here it is again. Yeah, you can see water coming through the flume in 2 distinct periods, one during the day, one at night. And then here, there's a second video here this past fall, and you'll see some leaves falling and then rain coming followed by runoff occurring. So hopefully everyone can see this. Sometimes these videos lag a little bit over Zoom. Okay, so when we take that data, we take that flow rate data, the samples that we took are the auto sampler, and we can calculate the loads, the pollutant loads. Of, in this case, we're looking at phosphorus. Here's an example of how we do that. So this storm occurred August 9th, 2021, was just about 2 inches of rain, resulted in almost 4,000 gallons of runoff. That was about 600 gallons per acre, and that was about only 1% of the rainfall resulted in runoff. But what we do is we actually, if you take a look at the graphs on the left, you'll see a series of panels over time. Top is precipitation and inverted axis every 5 minutes. Then we have total phosphorus levels, milligrams per liter, total suspended solid levels, milligrams per liter, and then phosphorus loading rate and flow rate, gallons per minute over time. Now, so the blue, if you look at the flow rate graph in the bottom left, you'll see the blue area is the flow rate of water over time through the monitoring station. What we do is we calculate the total volume of runoff, which is the area, the blue shaded area. So the area under the curve of flow rate is volume. And so we calculate that volume and we multiply it by the average of our samples. In this case, the example is showing total phosphorus. So the event mean concentration, because we're doing flow weighted samples and each sample corresponds to a specific volume of stormwater, we can average those together to create the calculate the event mean concentration. In this case, it was 0.7 milligrams per liter. We multiply that by the total volume in liters, and we can calculate the load of phosphorus lost. Here in this one event, we had about 10 grams of phosphorus lost, and that was about 0.004 kilograms of phosphorus per hectare. And this is just one event. And so the idea is to calculate this and add up all of the phosphorus or nitrogen or carbon or anything else over the entire year or multiple years and see how these pollutant dynamics are changing as time passes, as different seasons pass and different parts of the growing season come and go. Here's an example of some data now. We'll talk about the Caroline County catchment, which is a very large drainage area, as we said before, 140 acres. The map on the left is showing different shaded regions. So the black area and the perimeter is the watershed boundary. Again, everything is draining to a central ditch. And there's tile drainage that's draining from these different shaded colored regions into that ditch. And the map on the right, as we saw before, is the land use. Now we have 140 acres, soil phosphorus levels around 200 FIV. Again, corn soybean rotation, also alfalfa. Here's a video of what it looks like when a storm passes through this station. This is looking from the outlet. This was just this past month. And the storm occurs overnight. And so you can kind of see the swelling of water in the ditch if you look closely. And so this was a multi-day situation here. And the eastern shore, there can be a longer period of runoff. We're looking at not just surface runoff, but runoff through tile drains and ditches. It can take a longer time for that water to exit the fields. Okay, so here's the hydrograph from a storm in January of this year. And you can see the top figure is showing flow rate over time. And there's precipitation and cumulative precipitation that correspond to the inverted axis on the right. And then on the bottom, you're seeing when samples were taken. Again, flow rate over time on the left y-axis, but then on the right y-axis, you're seeing concentration of the different pollutants of interest. So we have the green circles are showing nitrate, the orange circles are showing phosphate, purple is DOC. And just as we did before at the PG site, we can calculate the load of each pollutant. And here we have about 1 kilogram of nitrate lost, about half a kilogram of phosphate, and about 15 kilograms of DOC. And then their corresponding loads per hectare. What's interesting is taking a look at the inner storm trends in pollutants. You can see there's kind of an initial peak in nitrate, and then it dips down and then increases again as flow rate decreases. Nitrate seems to be inversely proportional to flow rate, whereas phosphate stayed relatively constant or potentially peaked a little bit during the flow rate, and DOC seemed to peak a little bit early on in concentration and leveled out. It's interesting to look at these trends over the storm and see what we can learn about the fate and transport of these pollutants and the sources of these pollutants from the watershed. Finally, here's the third site we'll talk about. This is a tile drained site in Dorchester County, about 100-acre catchment, soil P level 200 to 250 FIV, corn soybean rotation. What's interesting here is we have mapped out the tile drainage in this field. And so in this catchment, we had 2 types of tile drainage. The purple lines are showing a dense underground tile network about 3 feet deep. They are conveying water to this orange outlet here. And then there's also, in connection with the dense network, there's a blind inlet network, which is, blind inlet is essentially a type of tile drainage practice where you have a surface opening. It's essentially a gravel pit that allows for surface water to enter into this larger diameter blind inlet pipe. The 2 tiles, the purple and green lines, are connected at the orange outlet where we're monitoring. So here's the hydrograph from that same January storm that we saw from the Caroline site. Now at the Dorchester site, tile drainage. Again, we have the hydrograph showing flow rate, gallons per minute, and then rainfall. We had about just over 1 inch of rain here at this Dorchester site. And then again, we have the concentrations. Here there were just 5 samples taken over time showing nitrate, phosphate, DOC concentrations. Similar trends here for nitrate and phosphate. Again, nitrates was inversely proportional to nitrate concentration was inversely proportional to flow rate. Phosphate seemed to be slightly proportional to flow rate. And DOC is a little different here. We're showing a lag in DOC concentration towards the end of the storm. Now, we were just able to sample 5 times because the sampling, as you can imagine, is difficult. It depends on an unpredictable amount of rain and runoff, and we don't always know how much runoff to expect. So we are programming the sampler to take samples at a given volume increment, but sometimes we might not get as many samples, or we might get too many samples and we can't cover the whole storm. So it's tricky, it's a hard balance. So here we just got 5 samples. But again, we're able to calculate the loads. Here little bit higher load, slightly higher than the Caroline site. Over a kilogram of nitrate, 0.6 kilograms ortho P, and then DOC was 7.6. And when you look at it as kilograms per hectare, these numbers for nitrogen and phosphorus, nitrate and phosphate are slightly higher per acreage than the Caroline site. Now, another thing that we're doing that's pretty interesting is we're using a new type of UVVis spectrophotometer sensor in the field sites. Now, we only have 2 of these sensors, but they're pretty exciting to us because what they do is they can take high temporal resolution water quality data in the field. And so when we're taking water quality samples using auto samplers, the traditional method, it can be very labor intensive and costly, as you can imagine. We have to take the samples, we have to drive out to the field sites. We don't necessarily know when there will be samples. And then we have to quickly take them back to the laboratory and preserve them until they can be analyzed. But with the in situ UVVis spectrophotometer, we can actually measure water quality levels in the field. And so it eliminates the need to carry samples back and use the lab to an extent. Now, the spectrophotometers are only able to measure certain parameters right now, but we're looking at potentially using them to expanding what they are capable of measuring. So we're currently collecting 5-minute data of nitrate, DOC, turbidity, and temperature at 2 of the field sites. The 2 we just talked about, the Dorchester site and the Caroline County site.
Hey Charles, sorry to interject, but I think we need to wrap up in the next 2-3 minutes. There's a class coming in the room. So if you can just
no problem.
Sorry.
All right, so just quickly, just to wrap this up. Yes, so we have some SCAN sensor data. The sensors are called SCAN sensors, and we're comparing the sensor data to the sampler data to see differences. There's some interesting differences. We can see more parts of the storm, and there can be some differences in the way they calculated loads. And then here's an example, some more different types of data you can get from the SCAN sensors. DOC, TOC, temperature, turbidity over time, high resolution. And you can see it shows you a lot more than just 5 samples would compared to the other samplers. All right, now Gurpal, if you want to take over for the final slides.
Yeah, I'm just gonna take 10 seconds. So we are pursuing other work in these connected catchment. This is another example. We're looking at phosphorus minerals that exist in the field. There's another paper on review. Next slide, Charles. So here we're using another very powerful technique, FTICR-MS, to sort of look at the nature of the molecular composition of the dissolved organic nitrogen and dissolved organic phosphorus compounds. This is again in one of our catchment, R1, R2. This is our site 14, 15, if you remember. So that's where we're looking. We're pursuing some other sort of side projects connected with this. Next slide, Charles. And I just want to take like a minute to talk about here. So some of the other things that we are interesting, and some of things are already in motion, is that one thing we are realizing is that we need more instrumentation in field sites. We are just looking at the outlet. So our plan is we're going to go into the Vado zone and install soil sensors looking at electrical conductivity, water temperature. We're also going to install suction cup lysimeters so we can actually capture the soil water that's leaving the field. We're also going to install some groundwater wells so we can capture what's happening in the sort of a catchment system. Next, Charles. And another, we are investigating some options, actually previous slide. So again, we're also investigating possibilities to remotely control these sites, which is pretty exciting. We have bought some data loggers that we think might work. There's a drainage water management. Some of the tile walls that we have can be remotely controlled. We're also plugging in our UVVis as well as our auto sampler into the data logger so we can remotely access data. That's one purpose. I think it also presents an opportunity to use some of machine learning or advanced statistics to see what type of decision support tools can we develop. Is there anything that we can give farmers in real time? And that's one of the goals. We're going to expand the real-time in situ sensor. We're looking for money. If you have sent Charles or me an email. And I think one of the main goal here is that this is an opportunity. The way I see is for my colleagues in the department and out of Maryland and other people to sort of think about what other things can we do together. We are pursuing some little bit efforts on soil organic carbon. We are doing a little bit of modeling. We are interested in advanced analytical techniques. Dissolved organic matter is exciting. We want to look at metals and phosphorus interactions, organic contaminants, insecticides, the whole thing. We don't have the expertise, but you do. So think about if there is something that was exciting to you and you are interested in collaborating with us. And Charles, next slide. And I think this is like another way to sort of visualize it. Charles, if you can go to next slide. So, think about catchment. Observatory is a box, right? So there are things coming in and things leaving. It's like, your bank account. There's the stuff that's being deposited and stuff that's being gone out. And we're interested in terms of keeping nutrients in the soil because that's to the benefit of the farmer. But there's a lot of other possibilities that this type of sort of, a facility provides. So think about it. Let us know if there is anything that's exciting. And I know, Marty, I'm sorry we took longer. We didn't realize there are other people coming in the room. So unfortunately, I don't think we have time for any of the questions, but we're happy to pick on one-on-one or group conversations with folks who have an interest.
I want to say thank you very much to Gurpal and Charles. Great study. Going to get some fantastic data, I can tell. And I'm sure there'd be lots of interesting questions from folks online and in the room. But we want to be good citizens here. And there's a class, I'm sure, in the hall waiting to come in. So thank you again. And this will be recorded. We'll let you know where the link is if you want to share it with others too. Thanks again.
Thanks, Marty. Thanks, Jared. See you later.
Thank you.
Thanks, Gurpal. Thanks, Charles.